All right, so now we get to start what I'm going to call Act 2 of the course, which is the laws of motion. So we're thinking less about how to describe motion. That's what we've been spending the first 13 or so lectures on. Now we're thinking about the reasons for motion. Why is motion occur? Something is happening when I throw a ball up into the air that causes it to first go up into the air, and then something else causes it to eventually fall back down. Now we're going to ask why this is all occurring. And all of this comes down to, for essentially the rest of the course, we will be thinking about how we can understand motion in the universe using Isaac Newton's 3 laws of motion. So, let's see. Let us begin. The history of science really is not really covered in a course like this. But Isaac Newton, if you ever have to read a book about a scientist, Isaac Newton had a fairly interesting life. And he's one of those people that he just existed on an entirely different plane compared to everyone else. He's just one of those people that just was so far above what anyone else could be that it was, I imagine, very hard from a social standpoint being Isaac Newton. For example, I could think of, what did Isaac Newton do? Okay, so he does his usual schooling, and then in 1661 goes to Cambridge University. While he's studying at Cambridge, he has to flee Cambridge because of the plague. But how does he spend this spring break of his? He invents calculus, develops his universal law of gravity, develops the 3 laws of motion that we're going to start doing, and begins his optical studies, which is the other kind of branch of physics that he's very well known for, while on break from school. I actually, in between, I graduated from Northwestern, got my undergrad there, and then I did my grad school at UC Berkeley. But the year between those two parts of my life, I did a master's degree in Cambridge, same Cambridge in England. And I must say I was not nearly as productive as Isaac Newton was. I perhaps went to the pub a little, perhaps too many times, rather than focusing on my studies, just because I thought that was what you did in England. It's pub culture, I thought, in England. Isaac Newton had this phrase that I have gone so far only because I have stood on the shoulders of giants. And it's usually interpreted to mean that he was able to do what he was able to do because he is building off of the work that has previously been done. So he was, people view that as an acknowledgement of Galileo, of Aristotle, of a lot of the, Kepler and Tycho, and all these scientists that have laid the foundations that allowed Isaac Newton to come up with these, for example, 3 laws of motion. It's not that that these just came out of nowhere. By saying that Isaac Newton came up with the 3 laws, it's not that he started from nothing and then just suddenly one day decided, what, these 3 laws, they sound good, I'm going to publish them. One of Newton's laws, really, Galileo was one of the first people to state the idea that we now know as Newton's first law of motion, that objects in motion tend to stay in motion. Galileo had done studies about this before Isaac Newton. But then Isaac Newton, building off what Galileo and others had done, he was the one that made the connections and saw that these seemingly disparate ideas in physics could actually be worked together. And if he wrote them down as the 3 laws that he did, that was the most general, most applicable way to describe what a lot of people were describing, but each using their own words and ideas, and they were focusing on various tiny little aspects of physics, where Isaac Newton kind of saw the forest from the trees and was able to see, what is the bigger picture here. And the same thing is true with Einstein and the laws of relativity. It, again, is not that he just one day decided that everything is relative and that relativity is actually how you describe the world. Again, it was building off of the results of Maxwell and electromagnetism, which is most of Physics 3, that there are things in electromagnetism that raise a lot of questions that Isaac Newton would have gotten wrong based on his ideas. So then Einstein had to go about and build upon it. That said, again, what am I, and then what else am I saying here? It might have sounded like I just said that Isaac Newton's laws of motion are wrong, yet we're going to spend the rest of class talking about, or the rest of the semester talking about them. And what I mean there is that it is true that Isaac Newton's laws are incomplete, in that sometimes Isaac Newton's laws give you the wrong answer. But that only occurs when you are, for example, moving very close to the speed of light, or if you happen to be hanging out near, an object like a black hole or something like that. Where these very extreme environments, it turns out that Isaac Newton's laws of motion are not able to perfectly describe the data that we observe. So Einstein's kind of insight was that he could take Newton and build upon it in a way, such that he just generalized it and made it even more applicable to more of the universe. If you were to do relativity and use the way more complex equations of relativity to understand how, say, a ball falls towards my hand, you would get the right answer, and you would get the same answer that Isaac Newton's equations would give you. The idea here is that Isaac Newton's equations are perfectly appropriate and perfectly applicable as long as you know the limits that they apply in. And for human society, Newton's laws apply for essentially everything that we do, unless you are getting into like electronics and quantum mechanics and that stuff. Then you have to be a little bit more careful. But in terms of flying balls and airplanes and the rotating Earth, and even like all my research, I study how stars form. None of that requires me to take relativity into account because I'm never dealing with things like black holes or nothing's moving close to the speed of light. So I use Isaac Newton's laws of motion to understand all these things. And know I can do so without making any substantial mistakes. So I do not want you to think that, since relativity is supposed to build upon and do better than Isaac Newton's laws, that means Isaac Newton's laws do not have a place. And we will essentially see that they have incredible and widely ranging predictive power in all that we do. In Physics 1 and a lot of Physics 3. That was a tangent. So I was talking about how I studied at Cambridge and that Newton had said the comment that he has come so far only to stand on the shoulders of giants. And people think that he meant to say that in a way that he was complimenting the scientists that came before him. Actually, there's some historians that think he actually was using that as a jab toward his arch nemesis, Robert Hooke, of Hooke's Law fame, if you've studied springs, and we'll see Hooke's Law in this course later on. Because apparently Newton and Hooke were arch nemeses, and they were both working towards, these laws of motion. And Robert Hooke actually claimed, he had made the claim that he actually came up with these three laws first, and not Isaac Newton. So some believe that actually Isaac Newton was making this comment, I have come so far only because I've stood on the shoulders of giants, as both a slight to Robert Hooke because he was not acknowledging Robert Hooke as one of those giants, and apparently Robert Hooke was incredibly, incredibly short for a man. So by highlighting giants, he was also calling attention to the fact that Robert Hooke was a short individual. It's also kind of a nice anecdote because it shows that even, scientists that are, super famous scientists are also human, and they also can sometimes be a little petty. But yeah, the year I studied in Cambridge was not quite as productive. I cannot say I have really changed the field of physics. I was able to stand near and close to people who have changed the field of physics. At that time, Stephen Hawking was the Lucasian Professor of Mathematics, which is the position that Isaac Newton held when he was at Cambridge after coming up with gravity and the laws of motion and whatnot. So I've at least been in the proximity of giants, though I may not necessarily be standing on their shoulders. Anyway. So what else did Isaac Newton do? Right, he became the Lucasian Professor, which is essentially, the a high-ranking position in the mathematics department at Cambridge. He invents the reflecting telescope. Most major telescopes these days are based on the reflecting telescope. Publishes the Principia, which is where the 3 laws of motion appear, and also his law of gravity. Then kind of has a nervous breakdown, flees the university, and actually then starts to work for the government. He becomes warden of the mint. Eventually returns to science while doing his warden duties, publishes his optics studies. And then ultimately he is knighted, but not for anything he did for science. He's knighted because he apparently was really good at his job as the warden of the mint. And apparently, right, there's also an anecdote that apparently one of the tasks Isaac Newton had to do as warden of the mint is that he had to decide punishments for people who, say, made counterfeit money, for example. And apparently the history goes that he apparently took incredibly immense pleasure in punishing people who try to steal from the mint or try to print fake money and whatnot. So whatever that means. Anyway, kind of an interesting guy. But what we will be focusing on is really these 3 laws of motion here. And we'll talk about each of them individually and spend a lot of time, particularly with the second and third one. Right, the first law is sometimes called the law of inertia, that if no forces act on a body, its speed and direction stay constant. An object that is in motion prefers to stay in motion. The second is his famous force equals mass times acceleration equation. So that is kind of being quantitative about how forces relate to accelerations. That is kind of the math version of something that also is mentioned in the first law. The first law is saying if there are no forces, then the velocity is not changing. We know that velocities change because of accelerations. So this makes the connection that forces imply accelerations. And we will see that in the next coming lectures. Then his third law is the action-reaction law, that when I punch the wall punches back. That when 2 bodies interact, they exert equal and opposite forces on one another. And we will see later on in the course, actually, that this third law is equivalent. It is the same thing as something else called the conservation of momentum. The conservation of momentum in the third law are actually, you can show it, and you can prove this, that they are actually saying the same exact thing. All right. So in thinking about forces, accelerations, all these things that relate to Isaac Newton's 3 laws, we are ultimately asking about how things move, why things move. And a lot of students find this part of the course very challenging, both from a conceptual point of view and just a quantitative point of view, because now we're taking everything we've learned and now we're actually solving more, in my opinion, more interesting problems. But it is all based on vectors, acceleration, velocities, positions, and being able to manipulate all of that with ease. So everything you've seen, for exam 1 is going to constantly reappear and reappear again for the rest of the course. Conceptually, it can be quite challenging because you are all going to find that you all have very deeply rooted misconceptions about how the universe works. A lot of these misconceptions arise because of everyday experiences where it seems like something is happening, but without really the proper education of how to think about these things, you've come to conclusions that are not quite appropriate. So, and you're in good company. Aristotle had a lot of misconceptions about how the universe works. When Aristotle came up with his laws of motion, one of his laws of motion was that an object's natural tendency is to be at rest. If things are moving, they will naturally try to evolve to be at some sort of state that is not moving. And again, you can't hold it against him because this does really jive with everyday experience. I take, my car keys and I push them across the table, give them some motion. They have a tendency to eventually come to rest. I push my mouse across the screen, or across the table rather, it eventually comes to rest, in that case pretty quickly. So it seems that no matter what you do, I throw a ball. I need that ball actually. I throw this racquetball over and it falls onto the carpet, rolls around for a bit, eventually comes to rest. So it seems natural that you might think that the natural state of things is to have something come to rest. Now we know, of course, that that is a result of a friction force bringing the object to rest, and not that the object wants to naturally evolve to be at rest. So the first law of Newton's laws actually, can be fairly unintuitive. It's saying that if there is no force acting on the object, it will continue moving at a constant speed for the rest of time. Which we have very few examples of that in the world. So if that seems odd to you, it should. But by working through these examples, seeing how experiments support the data and these ideas that we're going to be talking about, we're going to work through these misconceptions and work towards a position where we can think more critically and solve more complicated problems. Let's go through a couple more examples. Suppose you, or rather read these and see which one of these you think are true and which one of these you think are false. I should have refilled that. All right. Motion means that a force acts on an object. That suggests it means that if something is moving, that means a force is acting on it. Without forces, the corollary, I guess, without forces, objects will approach a state of rest. We just talked about that. The velocity of an object correlates to the force acting on it. If I'm acting with a stronger force on a ball, the ball will move faster or have a faster velocity. That's what that's suggesting. A force is imparted to the object to give it motion. So when I throw a ball, I'm imparting something to the ball to give it. I'm imparting, in this case, I'm a force to the object to give it motion. Not a single one of these is correct. So if you thought that any of those were true, again, you're in good company. And we will spend the next probably 7 or so lectures really digging into Newton's laws and thinking about why these statements are actually quite flawed. Motion means a force acts on an object. We just talked, Newton's first law says that no forces means you just coast at a constant velocity. So you don't need a force to stay in motion. Newton's second law is talking about how forces relate to acceleration, not velocity. And a force is something that is done to an object, we will learn, not something that is given to an object. Here's a couple others. Which of these do you think are correct, and which of these do you think are incorrect? A force must overcome the inertia force to move an object. So it seems like I have to work a little bit harder to get a heavy stack of books moving across my desk. And then once it starts moving, I have an easier time keeping it moving. Weightlessness is when there's no force acting on the object, so maybe when you're out in space. During a collision of a semi-truck and a car, the semi-truck exerts more force on the car than the car on the semi-truck. The semi-truck is bigger. If I were to see that collision on a road, the car would be worse for wear than the semi-truck, so maybe it's because the semi-truck is exerting more force on the car. Again, every single one of these is wrong. So again, do not panic if you thought any of those were correct, because these are misconceptions you have had rooted since your birth, essentially. Your everyday life has been rooting these misconceptions over and over and over again. But with a slight change of mindset in how we view the world, how we understand the world, what sort of words we use to describe what's going on, hopefully we will come to see that why these conceptions and ideas are flawed. All right, so there's nothing quantitative about this lecture today. Right now, we're just thinking about ideas. All right, so All of this hinges on the idea of a force. Newton's laws are all about how forces cause motion. Forces are the reasons why change in motion occurs. So let us build up a definition. Of what force actually is. Here's my first version. A force is a push or a pull. A force is a push or a pull. This would have been something we do in class, so I will encourage you to find a roommate or a family member or someone, or just do it to yourself. Find someone, you pull on their arm. So find them, hold hands, pull on someone's arm, and ask them if they feel something. You can pull on your own arm and ask if you feel something pulling on your arm. You feel, if you want to feel a force, you feel something going on to your arm as you pull it. Push against someone's face. Put your finger up to your face and just push against your cheek. I can tell that something is pushing me on my face. I'm feeling a force. I'm feeling either a push or a pull. Sometimes, with pushes and pulls, motion occurs as a result. I could have, my headphones. I could give it a push, and in this case, a little bit of motion does occur as a result by me pushing on it. That doesn't always have to happen. I could go up to the wall and I could push on the wall. But in this case, the wall does not appear to move. I can still feel myself exerting a force on the wall. If I do that for long enough, I will get pretty tired. I can feel myself exerting a force. Though that force, the force against the wall, did not necessarily result in any motion, where a force exerted to my headphones did result in some motion. So, is a push or a pull. Sometimes there's motion. Sometimes not. A force does not imply that something necessarily has to start moving. Again, sometimes it does. Sometimes the cause of the force is not the immediate cause that is creating the force. So the demo that I would have done is I would have had a rope where I would have asked one student to hold on to the rope while I held on to the other side of the rope. And then I would have pulled on the rope and asked if the student felt if they were feeling anything. And I think your intuition would agree with me that the student would have answered, yes, I can feel you pulling on the rope. But in that case, we can ask, what is the student feeling and how does it relate to what I'm doing to the rope? I am touching the rope. I am not touching the student. So as I pull on the rope, what's really going on is the rope is then pulling on the student. The student is connected to the rope and is touching the rope, and that's what they feel. Like if they were to wrap the rope around their arm and I then start pulling the rope, they would feel a tightening around their wrist or their arm, and so they would agree that they're feeling a force where the rope is. Even though the reason that the rope feels tight around their arm is not just because that's what the rope feels like doing, it's because I'm pulling on the rope and causing the rope to do that to the person. There is a cause for the force. So that is called an agent. My second definition. A force is a push or a pull from an agent. I meant to make agent green. Something has to exert a force, whether it's a push or a pull. So, for example, forces can often be exerted by animate individuals. I could push against you, and I am exerting a force on you, and that force is coming from me, an animate individual, a living being. But don't get into any confusion that forces require a living being. Forces can also be exerted by inanimate objects. My kind of favorite, simplest example is a spring. One thing we could have done in class is if I had a spring, I could have had, one student hold their hand up, I hold my other hand up, or they could just hold their own hands up with each other, and they try to compress the spring. Or if I press the spring and then they compress the spring, we would both agree that we are feeling a force from the spring. The spring is trying to retract itself back out. It is trying to push itself outward, even though we are trying to compress it. So there is a force coming from the spring as it tries to stretch itself back out. You can even kind of see the marks that are being left on my hand from the force this spring is creating. So forces appear to arise, in this case for a spring, it appears to arise when the spring changes shape. Something is going on about the spring that it wants to return to its former shape. So even inanimate objects can exert forces. We haven't really talked about gravity and what gravity is, but gravity, of course, there's no, Father Earth somewhere that is pulling on everyone on Earth. It is the inanimate Earth itself that is pulling down on everything that lives on the Earth, for example. Let's see, what other things do I have? Where's my little spring? Right, so that was an example of compressing a spring. We felt a force that the spring wanted to come back outwards and uncompress itself. The spring is a great example because it also can go both ways. Here's a spring that is initially compressed, and I can pull it out, and when I let go, it tries to return back to its normal state. So for the example, in this case, where I have an apple, if I were to let go, obviously it would just fall to the ground. But if I hang it on the spring, you can see that the spring extends a bit. My camera's not big enough, but then the apple has stopped just plummeting towards the ground. It now seems to be somewhat stationary in the vertical direction. As a result, the spring appears to be stretched more than it was when there was no apple hanging from the spring. So in this case, it appears like the spring is exerting a force on the apple. In this case, I would say the apple, it appears to be pointed upwards. Because in this case, the apple is trying to fall down via gravity, but the spring is preventing it from doing so. The spring is nice because you can kind of give something to what is causing the force. The fact that you can see the spring, you can see the spring kind of stretch and compress, and you can relate that to, maybe because of that change in shape. That is where the force is coming from. But again, doesn't have to be the case. I think we could all agree that if I hung a large rope from the ceiling and then tied the rope around someone's waist and then dangled them in the air, you would agree that you are feeling a force from the rope. It would probably feel very uncomfortable around your stomach as you felt the rope pulling on your body. While gravity is trying to make you fall to the ground, but the rope is pulling on you with a force that's pulling upwards, and you would feel that force as the rope became very tight around your stomach or wherever we tied the rope. So just because you cannot necessarily see any action, or you don't see a person grunting as they push on something, or you don't see a spring stretching as a result, does not mean that there is no force being exerted by perhaps an inanimate object, like a rope or a string. And you could ask, well, this seems kind of just wishy-washy, like you're just making up terms. And what's really going on, with, for example, a rope? What really is happening for a rope? How can a rope exert a force? And actually, that's where the spring actually is great, because, the chemist may appreciate this. If I were to zoom in on this rope closer and closer and closer, and looked at the molecular bonds that are holding this rope together, the fact that the rope is a solid and not a gas or a liquid, there's bonds that are created at the molecular level that's holding all the atoms and molecules together. You can study molecular bonds in material as just a bunch of really tiny, tiny little springs. When you pull on a rope, sometimes you can notice this with rope. If you pull on a rope, sometimes you notice it can stretch a little bit, but then when you let go, the rope returns to its original shape, kind of like a spring. In this case, you could think of, large solid objects. They're solid, again, because of the molecular bonds that's kind of holding all the protons and whatnot together in the material. Those bonds can all easily be modeled, and that's how you would model them, as a bunch of tiny little springs that are attached to all the individual atoms and molecules. You see this as well, again, going back to inanimate objects. You see this as well with, for example, like a bookshelf. You could think, you place some books on a bookshelf. Is the bookshelf exerting a force on the books? And the right answer to conclude is yes, it does. And in the case where there's a lot of books, you can see that the bookshelf is starting to kind of bend a little bit. And then if you were to take all the books off, the bookshelf would return to its normal state. Again, like a spring. It's bending, but it's trying to bring itself back to where it started. So that desire to be, level rather than bent, creates a springy-like force, like what you feel when you press down on a spring and you feel it trying to push back out and restore itself to its original shape. That is really all that is going on when you look at solid objects. Solid objects, if you were to sit on a table, this is a demo I usually do, but it was too hard to do it on camera, where you can try this on your own if you have a laser pointer. You take a laser pointer, put it on a table, point it towards the wall, and have nothing on the table. Mark on the wall where the laser pointer hits, where the light actually hits. Then repeat the experiment while standing on the table. So again, point the laser pointer, keep it in the same spot on the table, point the laser pointer towards the wall, but now also stand on the table. You will see that the shape of the table does ever so slightly change. The laser pointer should be pointing in a slightly different location than it was before. Again, because the shape of the table is changing, it's being bent, and while it wants to remain straight, so like a spring, it's trying to restore itself back to being level, which then that force, that restoring force it's trying to do, is also the force that's holding you on the table. The fact that gravity is trying to pull you down towards the ground, but as I stand on a table, I don't sink through the table towards the ground, which is where gravity wants me to be. The table stops me from moving towards the ground. There must therefore be a force that is pushing me back up, that's holding me on the table, rather than just letting me sink through the table into the ground. So these agents can be animate or inanimate. And hopefully that gives you some examples of what actually is going on when we think about forces from inanimate objects. Next definition. In all of these examples, we've looked at springs, we've looked at ropes, we've looked at me pushing against the wall, and all have talked about how forces are being exerted by an agent that is in contact with the other object. So when I'm pushing on the wall, I'm exerting a force on the wall because I'm pushing on the wall physically. My hand is up against the wall, pushing against the wall. The spring is exerting a force on my hand because I am compressing the spring and am in contact with the spring via my palm. and so therefore I feel the force being exerted on my palm. There is a point of contact, and through that point of contact is where the force, the push and the pull, is exerted. So my next level of definition is, I might say, a force is a push or a pull from an agent but now we're going to build upon this that occurs at a point of contact. There is a point of contact. There must be some location where the force is being exerted via push or pull. Again, why, if I were to dangle you from the roof while you had a rope tied around your waist, you would feel the force from the rope primarily at your stomach, because that is the point of contact between the rope and you. So any force the rope is exerting on you is occurring at that point of contact, the rope tied around your waist. And while you don't, for example, feel, if I were to wrap the rope around your waist, you do not necessarily feel your feet being, tugged or pulled by the rope, because the rope is not in contact with your feet, given the description I just had. Similarly with the spring, going back to the spring, I can press it with my hands. I feel the force from the spring on my hand. But then once I stop being in contact with the spring, I no longer feel the force. I don't feel anything anymore on my hand. I'm pressing down with my thumb, but once I remove my thumb so it's not in contact with the spring, I no longer feel the spring pushing back on my thumb. There are a few exceptions. And these are called the long-range forces. There are a few forces in the universe where where the force can be exerted seemingly through air or through the vacuum, across space, where you do not need to be in contact with the object to feel a force from that object. We will only see one of these ever in this course, and that's gravity. I do not have to be in contact with the Earth in order to feel the gravitational pull from the Earth. This apple is not touching the Earth, but nonetheless falls towards the Earth because of gravity. Gravity is an example of a long-range force, one that can exert forces without needing a point of contact. And if that makes you uncomfortable, you are not alone. Most of the famous physicists of the last few centuries were very uncomfortable with the idea of long-range forces. That is actually what gave rise to a lot of things like space-time with relativity, the photon, the gravitron, and just the ideas of fields like the electric field, the magnetic field, which you'll learn about in Physics 3. Which I guess brings me up to what's the next ones. So electromagnetism. Is another example of a long-range force. We will never see that in this class. You will see it a lot in Physics 3, given that Physics 3 is called electromagnetism. So, wave a magnet around. You've seen, if you've ever played with magnets, that you can make objects move by holding a magnet close to it without the magnet necessarily touching the object. Again, this made a lot of people really uncomfortable. So like in the history of science, you may have heard about the ether experiments, where people really did not like the idea that you could transmit electromagnetic forces without some agent. There wanted to be an agent. So people came up with the idea that we are immersed in this giant ether. And the ether is what allowed there to be contact between electromagnetic objects and the forces they exerted. And then the Michelson-Morley experiment actually proved that the ether did not exist. It was perhaps one of the best null results in science. A science experiment where they found nothing, which actually was scientific evidence to justify that perhaps the ether was tomfoolery, which then has led to new ideas like the electric field, the magnetic field, the gravitational field, if you go into relativity. So you will see fields a lot in Physics 3. We will not see fields that much in Physics 1. We will take gravity more or less as a given and say that it is the one exception we will make in this course where forces do not require objects to be in contact. Everything else, friction, the fact I'm not sinking through my chair because the chair is pushing up on me, I hit a baseball with my bat and it goes flying, that all results in points of contact between me and the chair, the bat and the ball, etc. Gravity will be the only exception we allow in that case. All right, so did we have any more of these? No, I did not. All right, so my final definition, since it's the final one, I might even also give it a highlight. So I think we're going to stand with a force is an push or pull from an agent that occurs at a point of contact. You can even see, how does your book define it? If at all. I'm not seeing the word force in bold. So I am going to give up on this endeavor. All right, so we are going to define force as a push or pull from an agent that occurs at a point of contact. The one exception to the point of contact element is that gravity can reach across space and exert a force. There's still an agent. The Earth is what is causing the gravity that makes this ball fall. The sun's gravity is what causes the Earth to continue orbiting around the sun. The force that we feel, the gravitational force, still has an agent that is causing it. But it doesn't necessarily require a point of contact. Now, let's start thinking a little bit about how this connects to what we will ultimately call Newton's laws. In some of those examples, like when I went up to the board and I pushed against the wall, that did not result in any motion. That is a great example of how force does not necessarily imply velocity. Let's even write that down. E.g., I push on a wall. Wall does not budge. Therefore, I might conclude forces do not imply velocity. If so, the fact I'm exerting a force on the wall should have caused the wall to have some velocity, but clearly it did not. And again, the confusion comes around because there are cases where I seem to exert a force and it causes an object to move. It seems to have some velocity, at least for a little bit of time. Of course, the right answer in that case is that the real answer is that my force caused the object to accelerate to have a velocity. But it's not the simple force equals velocity. The real answer is that force equals changes in velocity, perhaps. So we can also try to, so the tricky thing here is that also, like, especially if I'm trying to do experiments in my office, I have to constantly be dealing with the fact that there's gravity around, and it's hard to kind of isolate ourselves to only deal with individual forces. So the approach here that I'm going to try to do is I'm going to use one of our lab air tracks. So again, we've seen this in other demos. This is an air track that kind of causes the little red disc to levitate on a cushion of air so that it can move around with no friction. Everything is in the horizontal direction, so I don't have to worry about gravity. And we can do a couple small little experiments to see how forces, which are pushes and pulls, that's as sophisticated as we've gotten in terms of defining forces, pushes and pulls, that by exerting pushes and pulls on this red disc that is moving only in the horizontal direction, we can show that forces connect to acceleration and not velocity. So let me do the first experiment, which is where I have this little red disc, and I'm going to give it a nudge at the beginning, and then I'm going to take my hands away. So I'm not going to exert any force on the object except just to get it moving. And then once it's free from my hand and I'm no longer exerting a force on the object because there's no point of contact, we're going to look at what the velocity of that air track little cart looks like. So this is the case where I've given it a little push and then it traveled, for some distance. It eventually hit the edge and bounced. There was then a force at the edge here that pushed it back in the other direction. But just looking at as it was traveling if we're looking on the screen, from the left to the right, I exert a force, get it moving, it then moves at with some motion. I will now do the experiment again, but through the power of video editing, I will put a little green dot at points that are equally spaced in time. I think I did it at a tenth of a second. Oh dear, I'm so sorry. Did you catch that? So here we're going to do it again, and now I'm going to put little green dots. Let me do it again. So again, I'm putting green dots that appear every tenth of a second after I push it, after I'm no longer touching it. So thinking back to, what was this, lecture 3, when we defined displacements and how that connected to velocities. Since these points are equally spaced in time, I could measure the distance between them and get an average velocity by dividing by the time elapsed. And since they are equally spaced in time, that implies that the velocity is constant between the individual points. So it appears like when the object is just moving on its own, without any forces acting on it in the horizontal direction, it moves at a constant velocity. If this air track were, 1,000,000 miles long, it would be able to continue moving at a constant velocity, essentially forever. So that ties into what we are getting with in terms of Newton's first law. Now I'm going to do, that is my headphones, not the mouse. Now I'm going to do the experiment again, but now instead of exerting no force on the object, what I'm going to do is I'm going to take the spring and I'm going to connect it to the edge of the air cart and pull on the cart with a constant force. Now you might ask, how can you tell that it's a constant force? Well, again, here's why I love springs. With springs, it's easy to tell that the more you press on the spring, the more force you feel. That, the more compressed it becomes, the more painful it becomes on my thumb, a result of there being an even more force the more the spring becomes compressed. So even if I don't know exactly what to call force or what units to give force, I can calibrate a spring. This spring you probably won't be able to see it, but it has a little graduated set of tick marks that I can use as a sense of measuring how much force I'm exerting on the object. As long as I hold it so that the spring is stretched or compressed by the same amount and remains compressed or stretched by that same amount, I can be assured that the spring, therefore, is exerting a constant tug or pull on the object it's touching. So that is what I do here. So I have exactly this. You can see I'm hooking it up to the cart, and I'm going to pull on the object so that the spring is stretched by a fixed amount. And again, I will lay down green dots equally spaced in time as I do that. So here we go. So that motion looks a little bit different. The dots are not equally spaced as they were when there was no force. Now I'm exerting a force, and it seems like the dots started close and got farther and farther apart, which recall that was an example that we called speeding up, or in this case, accelerating to faster velocities. I do it again, but I use a more refined time. So you look at the initially in a tenth of a second or whatever it ended up being, the object moved very little, moved more, moved more, moved more, moved more, moved more. So as I was exerting a constant force throughout, it appears like you might think the position is changing, but the position is changing because the velocity is changing. I'm seeing the velocity increase from time element to time element, a result of the fact that the object is speeding up. So this air track experiment is showing us not that force is proportional to velocity. Oh, you can't see this. It's showing that it is not the case that force is proportional to velocity. Instead, it is implying instead that force may be proportional to acceleration. Because what I could do, and we won't bother doing this, but what I could do is I could go back and I could repeat this experiment again, but make sure I'm again pulling it so that the spring is compressed or stretched by a different amount, and see how the dots changed. And what you would find is if I pull it so that there's more of a spring force, so that it's stretching by more than it was previously, these green dots would become spaced apart even faster. It would appear like there would be an even larger acceleration as a result of me exerting a larger spring force on the object as I pulled. So that again is suggesting that force is proportional not to velocity but to acceleration. Forces imply acceleration. Forces imply that with a force, the velocity itself could change, which is, again, the definition of acceleration. And what you could do, let's see, let me make some tick marks. What we ultimately want to do is we want to write down an actual equation. Right now I've really just written down a proportionality. I've said force is related to acceleration. Double the force, double the acceleration. Cut the force in half, cut the acceleration in half. That's all a direct proportionality means. But really with a proportionality, an equivalent way of writing this is when I say two things are proportional to one another, that means they're related by something, usually a constant. So what this means is that the force is related to some constant times acceleration. That is equivalent to saying that force is proportional to acceleration. Because again, if it's just a constant, if I double the left-hand side, I'm doubling the right-hand side. If I double the right-hand side, I double the left-hand side. So the final task for today is to figure out what this constant of proportionality actually is. And this actually is going to get to us making a definition of a quantity that you are actually very familiar with, but this is actually how this quantity is defined. So what you might do in order to kind of prime your intuition that something is going on, right? You might notice, for example, if you were to go to an air track, or if you can actually do this if you have balls, like take a tennis ball, take a bowling ball. Have them both start from rest and try to exert a constant force on the ball. You might do that just by constantly slapping the ball, but try to always use the same slap every time. If you're slapping the ball, you'll notice the ball will start to roll, and it will start to roll faster and faster and faster as you continue to slap it and give it a constant force. Again, suggesting accelerations, not velocities. But I think your intuition probably could agree with me saying that if you're using the exact same slap on the basketball compared to the bowling ball, that it's going to take a lot more slapping in order to get the bowling ball to really get going. A gentle slap of the bowling ball will just make it rotate a little bit, where a gentle slap of a basketball might make it start rolling very quickly. And you're trying to do it so that the forces you're giving to the balls are the same for both. So the forces are the same in those cases, but the accelerations clearly are not. So you could ask yourself, what is different about the bowling ball versus the basketball that might be the reason why your slapping results in the basketball accelerating much more than, say, the bowling ball? And the bowling ball, I think you would agree, is much heavier than the basketball. So you could ask, maybe this is something related to how much stuff there is that makes up the object. And we could do a similar experiment like this on the air track. I could take the air track little disc, and actually, maybe I might actually go up and make this recording at some point. Let me get the dots out of the way. There are these little screws that are on both sides of the air track disc. So one thing you can do is you can put weights on top of the disc. So you can change how much stuff is being pushed around on the air track. So one thing you could do, for example, is I could, again, agree that I'm always going to pull the object with a constant force, that's extending the spring by a certain amount. But I could do it to different discs that have different amounts of weights put on it. And I could do this quantitatively. Maybe I use one weight, and then I do it with 2 weights, then I use it with 3 weights. So I'm systematically changing the amount of stuff on the disc, and I pull it with the same force. I could therefore then measure the acceleration I see. And I could then figure out what happens. So going back to this plot, let me just give you an example of what you would find. Because again, this is it's hard for me to do this experiment in my office. Suppose I do it for just the cart, like with the movies you saw. You might get something that looks like this. As you increase the force in the y-axis, you increase the resulting acceleration you observe. Now suppose I put one of those disky weights on it, and I now try to do the same exact experiment for different forces, measuring different accelerations. I might get something like this. So this had, 1 times the amount of stuff, and perhaps then I put a weight on it so that it's 2 times the amount of stuff. And I might get a curve that looks like that. Then if I put a third weight on top of the disk and do it again, I might get something that looks like this. So this might be 3 times the stuff on the AirTrack disk. And what you're seeing here is you're seeing that there's a relationship between the observed acceleration, so I'm observing it accelerating at some rate, and that's connecting to the amount of force I had to exert on the object. When there was only one amount of stuff on the object, I could get away with exerting a lower force, and as a result, I achieved some acceleration. Versus if I doubled the amount of stuff on the AirTrack, I had to exert twice as much force in order to get the same acceleration. And then similarly with 3 times the stuff, I had to have 3 times the force in order to get the same observed acceleration. So the more stuff there appears to be on the object, the more force is required in order to get a given acceleration. So this is actually how we define what I call, well, not what I call, what everyone calls, the inertial mass of an object. We say that the mass is whatever this thing I'm calling mass now, it is defined to be the proportionality between force and acceleration. That is the definition of mass, which allows us to write F equals ma. And again, we might have gotten to this equation in a way you did not expect us to. I did not prove F equals ma. I essentially declared F equals ma. And I declared F equals ma because this is actually how you define mass. Inertial mass is defined by this relationship. If you want to measure the amount of mass something has, you are essentially saying, okay, if I put it on an AirTrack and try to exert a force on it and measure the acceleration I get, the relationship between those two is this thing I'm calling mass. This is how you define the inertial mass of an object. And also holds the title of being called Newton's second law. Oops. Where Newton's first law, really I could come up here and say the fact, I could write the fact we were able to write these two things down, that forces result in accelerations, not velocities. That is, in a sense, an interpretation of Newton's first law. You can think of Newton's first law as the definition of a force. Newton's first law is telling you that changes in velocity occur through forces, or accelerations occur through forces. Newton's second law makes it more quantitative and says the relationship between force and acceleration is through this property we're going to call mass, so that F equals ma. This also allows us to quantitatively define force. I could ask, for example, what are the units of force? It therefore must be the units of ma, or the units of mass, times the unit of acceleration, or in MKS units, the kilogram times the meter per second squared. A unit of force is a unit of kilogram meter per second squared. Since forces come up so often, this unit therefore comes up so often, it is defined then as, this unit is defined as the Newton, or N. So 1 Newton of force is 1 kilogram meter per second squared of force. So that's good enough. Yeah, that's even worth a little bit of a highlight. All right. So now the idea is that we can think about, okay, we know where forces come from. Forces are pushes and pulls from an agent that occur through a point of contact, unless it's gravity. We have seen through experiment that forces cause accelerations, not velocities. If there are no forces, the velocity doesn't change, which means if the object is at rest, it will stay at rest. But it also means if the object is already moving, it will keep moving at that same velocity. Its direction will not change, its speed will not change. Newton's second law allows us to be more quantitative about this and write down that the relationship between force and acceleration is through the inertial mass of an object. Which allows us to write down Newton's second law for a given force. What I've written down here really is just for a single force, a single spring, pulling on an air track, for example. A spring pushing back on my hand. Obviously, it is more interesting if we can talk about cases where there are multiple forces occurring simultaneously. And so that we will look at superposition and multiple dimensions in the next lecture, where we will upgrade to multidimensional, multi-force motion. And then that gets us to the new challenge of being able to then solve problems using this expression.